Okay, hello everybody, and welcome to the first of our early career research series seminars. So this is a series of currently 3 planned events where we've got 2 early career researchers per event to talk about the interesting topics. So we have an hour. And we've got to effectively just under half an hour, 20-minute talk plus questions for each speaker. So my name's Mark Broom. The lead organizer of this session was really Amelia Herta Sanchez, but unfortunately she is unable to be here today. So I am her deputy for the session today. So I'm very happy to welcome our first speaker, who is Francois Bienvenu from the CNRS, and he is going to tell us about where do phylogenetic trees come from. So, Francois, when you're ready.
Yeah, I'm going to share my screen. Up, should be working, I think. Is it working for everyone? Or
I can see it. I see a little black rectangle which has now disappeared. So yeah, I certainly see a nice white screen.
Okay, perfect. So thanks a lot, Mark, for the introduction. And I should mention that I managed to go through all of COVID without giving a lot of online talks. And usually I give Blackboard talks. So today I wanted to try to kind of do the same thing online. And I really hope it's not going to turn to be a terrible idea that you and I are going to regret. But, well, we'll see. So the title of this talk is Where do phylogenetic trees come from? And as a spoiler, I'm not going to give you a lot of answers about this today. Instead, my goal is mostly to show you that even though we tend to take for granted the fact that evolution should be described with phylogenetic trees, this is actually not trivial, and it leads to a lot of interesting questions, both from a biological point of view and from a mathematical point of view. So maybe just so that we're all on the same page, I'm going to start by saying that, so as you all know, a tree is a network that has no loops, so it's an acyclic graph, but usually I'm going to be thinking about rooted trees here. So you have a root like this, so this special vertex, and then you have some branches like this. Okay, so something like this. And this kind of structure is, this kind of mathematical objects is very well adapted to describe a structure where you have a hierarchical structure. Because, for instance, if you label the leaves like this, so A, B, C, D, E, so then that gives you a set of nested groups. So for instance, here you would have A, B, C, D, E. So you could group here A and B, like so. So you have this group A and B. Here you have this group D and E, like this. And then this group here. So you have this nested collection of groups. And so when naturalists such as Linnaeus started describing living organisms, and they tried to inventory species, they realized that they seemed to fit nicely on such trees. And of course, at the time, they interpreted this tree structure as just being the way that God had chosen to keep everything neat and tidy. And so they didn't really need to explain where this tree came from. Then, with the theory of evolution, came the idea that this tree should be interpreted as representing the evolutionary history of the species. But then, when you say this on a superficial level, it gives the impression that we should obviously have a tree and there is not much to explain. Because, oh wait, actually I can't really see my screen. The Zoom window, okay, I'm going to put it here. Perfect. Okay, so if you say that the tree is going to represent the evolutionary history of species, it looks like you have to have a tree, because if you have so one group of populations A like this that you interpret as a species, and so time is going from top to bottom here. So what could happen is that at some point, some populations from A are going to become more and more different, up to a point where you will consider that they no longer belong to the same species as A, and then you will be able to say that the new species B comes from species A. And then again, some individuals from species B could differentiate and form a new species C, which is then going to come from species B. So it really looks like we have to have a tree, and there is nothing to explain here. What we need to explain instead is how group of populations become different and form new species. So basically speciation. So in other words, I've been wasting your time for about 4 minutes because there is nothing new here. It's not a new question. It's one of the central questions of evolutionary biology. We want to understand speciation. However, my point is that even though everybody knows what I just said, still, when we model evolution, we keep clinging to trees and we keep taking them for granted. So typically what we do is we usually use processes such as birth-death processes, where you have species that can spatiate or go extinct at some fixed rate that may vary in time or depend on some trait of the species, such as its size or its geographical position. But still, we view species as sort of a black box, and then we just use external elements to understand what is driving speciation and put this in the model. And so as a result, these kind of models, they can tell us a lot about the shape of phylogenies, and they can be extremely useful. Actually, they've already proved to be extremely useful. But the models themselves can give us limited insight on the speciation process. We really have, with this model, with this approach, we have to treat speciation as an external element, which we study using from a biological point of view, and then we plug it in the model. The goal of the kind of models that I would like to talk about today is to go sort of the other way around and stop taking species and the existence of a tree for granted, and instead recover it as an emergent property of the model. And I think that this approach should give us more understanding of speciation coming directly from the model, because then we're going to be able to identify the conditions under which there is the emergence of a large-scale structure in the evolutionary history, and conditions in which there is not going to be such a large-scale tree structure. So I should mention that I've recently contributed to a review on this question. So it's here. It was written by a PhD student, Elisa Couvert, who is a PhD student of Amaury Lambert. And so in this review, we've tried to list several models that take this approach, and to try to explain what each of these model, what is the advantage of each of this model. And we've also, in order that this review would not just be an ordered bag of models, we've tried to come up with a sort of general framework for classifying this model, which of course is imperfect, but at least it gives one, it gives a bit of structure to the review. So if you're interested in the kind of model that I'm about to present, you can have a look at this review. So now that I've said this, the first model that I'm going to present is actually a work that I did a while ago during my PhD. So it was published in 2009, and it's called the Split and Drifts Random Graph. So this is, first off, I should mention that this is a time model. And so here the main focus is going to be the mathematical tractability. It's not going to be how well the model can fit to real data. And I'm going to come back to this at the end of the presentation. And so the idea of the model is to model everything at the level of population. So that's the first idea, model at the level of populations. And then the second idea is that species should be based on the capacity that populations have to interbreed or not. So species are based on interbreeding. And so this is something that has sometimes been called the BSC, for the biological species concept. So once we say this, we're going to represent the state of the system by a graph whose vertices are going to be the populations, and where two vertices are going to be linked if the corresponding populations have the capacity to interbreed. So you're going to have some populations like this, maybe, and then all of these populations can interbreed like this. And then here, you're going to have another group of populations, so maybe, again, 4 of them. They can all interbreed, and you could have something like this. So this graph here contains all the information about the population relative to their interbreeding potential. But here we haven't specified a notion of species. So for instance, you could say that this graph of vertices here corresponds to sort of an ideal species, because here every population can interbreed with any other population from the group, and they cannot interbreed with other populations from other groups. But if you look at this group of populations here, it's not so clear, because if you group them like this, for instance, then you see that there are many populations in the same group that cannot interbreed, which maybe is not so nice, because we have the idea that if you belong to the same species, then you should be able to interbreed. And if we take stricter groups, so for instance, if we say that this is a group and this is a group, then we might have this problem that there is this hedge here. Here you have two populations that belong to different groups, and yet they can interbreed. So the graph is this object, this graph with the links that represents interfecundity, is the object that we want to study. And the model that we consider with Amaury Lambert and Florence Desbarres is the following. So we're going to say that the graph is a Markov chain, a continuous staff Markov chain that evolves according to 2 types of events. So the first type of events is going to be the splitting of population. And so that's going to correspond to a duplication of the vertices. So let's say that you have a graph like this, something like this. So at constant rate 1, what you're going to do is you're going to pick one of the populations uniformly at random, and then you're going to remove that population and replace it by a copy of another population, exactly like in the Moore model. So for instance, let's say here that I pick this population, and it's going to replace this population in blue by a copy of itself. So what happens is, first, I remove the population that gets killed. So this one disappears. And then I add a copy of the population that has just split. So I have a new population here like this. And then this population, initially, it should be completely identical to its mother population. So that means that it's also going to be linked to the neighbors of the mother population and to the mother population as well. So that's the first type of event, splitting of population at constant rates. And so the goal of this is to model what happens when you have just a population that divides into 2 subpopulations, because maybe one of them colonized the new environments or something like this. And then the second type of event is going to be that each edge is going to disappear at constant rate r. So each edge so you just have some edges, like the edges have a limited lifetime, and after a while they just disappear like this. So maybe, for instance, this edge disappear, and then maybe at some point this edge disappear, etc. So these two events define a dynamic random graph. As I said, it's a continuous time Markov chain. And actually, this continuous time Markov chain has a stationary distribution. And it turns out that from a mathematical point of view, we're able to say a lot about the structure and the geometry of the stationary distribution. And so mathematically, the way that we're able to understand, to gain some understanding on the structure of the stationary graph is by studying quantities such as the degree distribution. So that means if you take a vertex uniformly at random of the graph, what is the distribution of the number of neighbors that it's going to have, degree distribution. We can also study quantities such as the number of connected components, or other things such as the number of complete subgraphs of size k. So all these things are fairly explicit from a mathematical point of view. However, they're not really relevant from a biological point of view. But what you can do is you can study the other things from simulation. And for instance, in this model, once you've chosen definition of species, so for instance, let's say that you say, okay, species is going to correspond to a connected component in this graph. So that would mean that here, for instance, we have 3 species. So that's 1 species, 2 species, 3 species. So once you have chosen one such definition, then this graph is going to generate jointly the phylogeny of the species along with their abundances. So it gives you a lot of prediction on, the model gives you a lot of predictions on the following things. Things like speciation rates, shape of phylogenies, wait, I'm going to speciation rates, the shape of phylogenies, and also species abundance distribution. So as I said, it's a toy model, and here we try to keep the model as simple as possible. So for instance, the split happens at constant rate, and the edges also disappear at constant rates. And so as a result, these quantities actually make predictions. They do make quantitative predictions, but these quantitative predictions do not match the reality so well. So for instance, the shape of phylogenies in this model is going to be look a lot like Kingman trees. So it means that it's very balanced, which is not very realistic from a biological point of view. Similarly, the distribution of the species abundance is going to be very even. And so that's, again, not very realistic, because usually species abundance distributions are very unbalanced. So superficially, it looks like the model is not very satisfying. But the thing is, here we said that the speciation, the rate at which population splits is the same for all population, as is independence, for instance, of the number of neighbors of the populations or things like this, because we wanted to study the model from a mathematical point of view. But if you tweak the model a little bit and you allow more flexibility, so for instance, you could say that the rate at which population splits into 2 populations is going to depend on the number of populations with which it can interbreed, or things like this. So if you allow small tweaks in the model like this, then you can no longer study the model mathematically, at least not as much, but you can still get all these quantitative predictions by simulations, and then you can get predictions that are that fit the reality much better, and that give you more insights on the speciation process itself. So I think, so this model hasn't really been picked up by biologists, I guess because it's too simple, it's the toy model. But so I would like to kind of convince you that if you just make the model a tiny bit more complicated and tweak it a wee bit, then you get something that could be interesting for generating phylogenies and understanding how the species abundance is related to phylogenies, etc. So I should also mention that in case you're interested, this work was published in this article, so with Florence Debar and Amaury Lambert. So I see that I'm running a bit low on time, so I'm going to keep going a bit fast. So this model is nice because it kind of explains where the shape of the tree, of a phylogenetic tree is going to come from. However, it doesn't really tell us why we even have a phylogenetic tree, which was the original question in the talk. So the second type of model that I would like to present is a model where we do not assume that there is, so maybe I should mention why is the, well, in the model that I've just presented, the fact that there is going to be a phylogenetic tree is kind of built in the model. And the reason for this is that once you have two group of species that become completely reproductively isolated, so for instance, let's assume that you have this graph and then this edge disappear, then you obtain two groups like this, and there is no way in the model that you're going to be ever able to create a new edge between these two groups. So it means that by definition of the model, there is going to be some branching in the model, and so you should expect to see a tree. What's not clear is what the shape of the tree is going to be like, because that's going to depend on how you define species. But the fact that there is a tree is kind of inevitable. So the second type of model that I've been studying more recently with my colleague Jean-Gilles Duchamp, are models where you allow, you just describe what happens to a set of populations and you allow them to split, but also to merge. And of course, the rate at which population merge should decrease as the population become more different, because if you have two very closely related subpopulation of a species, it's quite likely that they could merge and form a new population, whereas if you have two completely different species, this cannot happen. But so the thing is, if you always allow the possibility that some population can merge and you just make it less likely as the population become more differentiated, then from a mathematical point of view, it's actually not obvious at all that there is going to be the emergence of a tree structure in the evolutionary history. So the kind of model that you could consider for this, for instance, could be the following. So you could consider a population that evolves in time. So again, here time is going from top to bottom. And you have population that just split to give rise to new population, like this. Sometimes they can also die. So far it's exactly as in a birth-death process. But then you also allow this population sometimes to merge to form a new population. So something like this. So here you have sort of a birth-death process with some extra coalescence events. So that's what we call a branching process with coalescence. And the thing is, you're free to choose your coalescence rate between populations. So for instance, you could say that each of these lineages carries some traits, and that the coalescence rate of two populations is going to depend on their traits. But what you could also say is, for instance, that the coalescence rate is going to be a decreasing function of the divergence time between the populations. So that's what we're going to do. Coalescence rate is a decreasing And the thing is, once you consider these models, the idea that you have is that if you look at the model from far away, if the coalescence rate decreases fast enough as a function of the T-MRCA, then you should have some sort of tree structure, some sort of large-scale tree structure. So something like this. You should have something like this. And then inside this, you have a very complicated network with a lot of things that just merge and split in all directions. But if you look at the network from far away, it should look like a tree. So
that's why you've had sort of about 24 minutes. So if you could sort of round up.
So I'm going to stop. Yeah. So I'm going to stop. I'm just going to say that we've been studying such models to try to identify some mathematical conditions under which we have the emergence of a tree structure. We have some fairly specific mathematical conjectures. So for instance, we have some necessary conditions for the emergence of a tree structure. We have some sufficient conditions. Of course, they don't match, so we don't really know what happens in between. But for instance, in this case, where the coalescence time is a decreasing function of the T-MRCA, we think that the threshold for speciation, so the threshold for emergence of a phylogenetic network, is exponential decay of the coalescence rate. So we have some fairly specific conjectures like this. And also, so with Jean-Gilles Duchamp, we've recently studied one such example of model where we cheat a bit and we kind of force the existence of a tree structure. And then in that case, we're able to completely characterize the phylogeny. So unfortunately, I'm way over time, so I'm going to stop here. I hope I've still managed to convince you that there are some interesting mathematical questions in these models that are kind of hard to tackle from a math point of view, but that are also relevant for biology because they really tell us not only what do phylogenetic trees look like, but also why we even have phylogenetic trees. So thanks, and sorry again for the time management.